How's the mic level? Is it okay? Cool.
You already started.
Hello everyone, welcome to the Copenhagen Ruby Brigade. Welcome, thank you. So, it's been a while since I've been at one, so it's great to see you all. Usual recap of what's happening this year. I think we've been relatively consistent with a meeting every month since, obviously since COVID. We're going to do our best to maintain that. Every second Wednesday, same time. Half the months it will be here, and maybe somewhere else, maybe your office on the odd months. We would love everyone to come and do a talk at some point. We always need speakers, so there are many things that are, very interesting and valid that people want to hear you talk about, even if you think it's something obvious or, not interesting to you. And there's a list here of stuff that we, just thought off the top of our heads might be interesting to talk about. I don't think we've updated this list in a while, have we? But still nobody has ticked all these off. So maybe have a quick read of that. And have a think about if you want to talk about one of these topics or something else. We have a code of conduct. This has been in force for a while now. We use the Berlin code of conduct because they put a lot of effort into theirs and it seemed good to us. We do this because we love our community, but no community is perfect, and we want everyone to have a good time. If you feel that someone is in violation of the code of conduct, please speak to myself or Chris, who is sat in the front row there, and we will try and do something about it. So please give us some feedback about the event today or any other past event. We would like to know about anything, but it could be accessibility issues, dietary requirements. You tell us. Thank you very much. So unfortunately, we only have one speaker tonight, but fortunately, it will be a good one. Ignacio, one of our other organisers, was going to give a remote talk from his home, but unfortunately we have an audio-visual problem here, which is going to make that impossible, I'm afraid. So, Aurora, are you ready?
Yeah, I'm ready.
Please welcome Aurora.
I'm going to joke about you getting a double feature of me, but that won't happen. So excellent. So I'm going to talk about domain-specific languages, because this is something that all of us use. Not every day, but So this is me. I have weird features. You can stream all my thoughts directly on the internet. And if you want to hire me or something, hit me up.
Question.
Yeah.
Has many sharks?
Yeah, I have many sharks.
Like in a fish tank at home?
In a rack of sharks. I'll show you pictures later if you come over. And if you have any questions at any point in time, I'm more of a just scream person than hand raising, so just feel free. I would like to thank you, Copenhagen Ruby Brigade. Your entire name did not fit on the slide, but the two thirds. Excellent. Thank you for inviting me. So this presentation, I won't teach you how to make your own programming language of any sort of, because that is not what we're going to do in 30 minutes. That's just not going to happen. But I think I'm going to give you all the hints that allows you to Google for stuff later, so you can make your own domain-specific language for whatever problems you have or create for yourself. So some of these techniques can be used outside of languages and just are stuff that's used in a lot of Ruby libraries to get nicer APIs. But what is a domain-specific language? It is a very overloaded term, especially in the Ruby community. So I think I've identified 3 senses of this word. The first sense is anything that's nice. Like people say like, oh, Rails is the domain-specific language. Then by that they mean Rails is nice. Like when someone says, I have a mechanical keyboard, they don't mean it's actually mechanical, they mean it's a nice keyboard. I paid a lot of money for it. Examples, like any library you actually like. RSpec might be a domain-specific language. I don't know what people like these days. But any library that you like. There is a second sense, which is probably the more traditional sense of domain-specific language, which is a programming language that you only use in a specific domain. The classic ones are SQL, R, Verilog, GLSL, Emacs Lisp, and so on. All the classic ones, like you don't use Emacs Lisp for any serious programming unless you're an Emacs person. Yeah, but you know, you can't write like an application GLSL. It's just not going to happen. You need something else. Same thing with SQL or R or Verilog or. But we often in the Ruby community use a third sense for domain-specific language, which is a language that borrows most of its implementation from its implementation language, which is like this is a programming language, but that we design the semantics or syntax of, but we're stealing most of it from Ruby because, you know, making our own programming language is hard. If you want a nice programming language, that takes years to make sometimes. And that's like a lot of hard work. We can just steal Ruby. Or another language, but in this presentation we'll, for example, Arel, Cucumber, Break, Rails migrations, they specify a language that we can write, and most of the implementation is Ruby. And then we don't have to write a parser, we don't have to write a lexer or all, I mean, in Cucumber you do, but never mind. So all of these languages steal a lot of stuff from Ruby. And that is what makes it important, because that means that we can implement like a useful programming language of some sort, even if it's a restricted subset of a language, in like a few hours. And that's pretty cool, right? It's like I wouldn't write my own programming language in a few hours if I didn't have Ruby. So some of these languages replace semantics, which means that the syntax is pretty close to Ruby, but the semantics are different. For example, in Arel, it looks exactly like Ruby, like it is Ruby, but it translates down to SQL that we send to a server and then it executes it. The semantics don't do anything that Ruby can do. We convert it into some other representation and then ship that off to get something done. Rake, the same thing. We write some almost Ruby, and then we have the rake binary do something with it. It's close to Ruby, but you can't just write normal Ruby and expect it to work in there. Stuff will happen, and it's usually not good. And unlike in RL, which is completely unusable, Rake actually is pretty nice. Most of us would probably prefer using Rake to make. That is the reason why we use Rake. While the reason why we use RL is not that this syntax is nice, it's actually complete bullshit. but it allows us to use the same code to run on multiple databases. That's why Rails uses ARL. And that is pretty cool because someone didn't follow the SQL standard because that was hard or something. I don't know. I'm a bit bitter about that. Some languages instead keep most of the Ruby semantics and just replace the entire syntax instead, like Cucumber. We have some text here that is obviously not Ruby, nothing this. So I have a scenario with some foxes, and if I have 3 foxes in my bedroom, I probably don't have a bedroom anymore. Then we can implement a thing here in Cucumber that adds Ruby semantics to whatever wrote in our scenario. And that is very useful for, stakeholders and so on, writing tests for you. And then you parse those and have tests. That's nice. So there are a lot of reasons to make these. These are some of our most common languages for a good reason. Both in volume and the most popular ones. Like SQL is probably the language that is running the most code in the world. Everyone writes SQL all the time, right? We generate SQL every minute. GLSL, we generate GLSL or DirectX shaders every time we start a game. There's so much code for these, just because they are convenient. You don't want to run C++ on the graphics card. Don't look at me, Apple. But most other graphics card makers do not run C++ on the graphics card. They prefer these domain-specific languages because historically, databases or graphics cards or FPGAs or so on were limited. And we have reasons to do that as well, because when we make our own language, we can make it specific for our use case. Maybe we use it to make business logic more clear, to say that you can only write these specific things and you can only make valid business logic written in this language. You can make it reusable, or like in ARL, you have many databases that you want to talk to with the same interface, but they all speak different languages. So you create something that allows you to speak to all of these databases at once. And that is what allows Rails to work with multiple databases, and a not insignificant amount of all Rails apps can just change database. Like, I don't think it's as common now, but when I started using Rails, a lot of people were using SQLite in test and Postgres in production. That is a pretty big jump. Like, the SQL in SQLite does not work in Postgres. They're slightly similar, but ARL bridges these domains, right? And that is like a superpower for Rails. Rails was the first major framework that had this, and it was usable. Of course, it was kind of like an anti-feature because people actually tried to move their apps from one database to another. It didn't end up well, but the fact that you can use any database you want is extremely valuable, even if you can't migrate your app between databases. So that is the reason why we really, really want to make our own languages. And if you have worked with any larger code base, you've probably seen these languages around. Enterprise tools have them. They have their own version of SQL, whatever SQL is. They have their own versions of query languages, of AppleScript. You can AppleScript anything, not anymore, but you used to. almost all of these major applications that you work with, they probably have some sort of scriptability built in that only works with that app. And being able to build these is often what separates like apps from the kiddie pool to the big enterprise apps. So we're going to have a bit of a workshop here. We're going to make our own domain-specific language. Like, we have this board that I forgot to program it for because I'm a little bit of a not that prepared apparently. But it's an FPGA. It's a field programmable gate array. It is a chip that can be converted into another chip. You flash it with information that connects the gates on this chip in a specific configuration. While these are completely regular chips. I'm going to show you. This is the chip that I'm holding in my hand, or I have a bunch of them. I can pass them around if anyone wants to have some chips. Do you want some chips? You can. Don't eat them, but otherwise you can do whatever you want with them.
Don't think of pink elephants.
You can have some more. So maybe some people want some. You can play with them. So these chips are. These chips are very simple. These are from the 60s, so they have 4 gates. They cost like a krona each, so they're fairly cheap, even these days. So we're going to take this chip that is way more expensive. It's about 25 euros or so, or at least for an entire board, and turn it into one of these very cheap chips. Using Ruby, because of course you want to program your chips in Ruby. Like who makes chips in like some sort of hardware design language? It's like, I use Ruby for everything. I mean, I didn't 2 days ago, but you know. So whatever domain-specific language is really needs is like you need a good foundation, and hate it or love it, we won't be able to fit the entire process of turning Ruby into a chip in this workshop. So we're going to have to use some foundations from some other things. So we're going to use a library called Joses. It is, I wish it was short for something reasonable, but it's short for the Joses Open Synthesis Suite. But it has a manual and some memes, so we have to do this first. I don't have any cat ears, so we'll have to settle for putting on some fox ears for this. But I'm sure it will work out. So yeah. So that's the Joses manual. Yeah. So this is the part where every presentation fails a little bit. So that's where we're going, right? We're going to see if. Oh, shit. This obviously worked exactly like I set it up. That was a mistake. Arrangement, mirror displays. Okay. Oh, excellent, except it's like extremely tiny. And this is also extremely tiny because of course it doesn't zoom both at once. Okay, so I wrote a little bit of a library here that can so what Joseph does, it takes something called RTL-IL. Okay, I'm realizing this is completely unreadable. That is slightly less unreadable. Excellent, excellent. So this chip that I showed you is called a 7400. It's part of the 7400 series, and it's a 74 LSO00. It contains a NOT AND gate. And this is the intermediate language that we're targeting. We want to generate this. And this is just the actual file, if we were going to look at that. Would look something like this, but I made a Ruby library for it, which is convenient. So it just says that, like, oh, we have a module. It's called 7400. It's got two wires that are inputs, A and B, and a wire that is an output. And then there's a wire that we just have internally because, well, then we have a cell. Every cell is like a very small part of the computation, and this is an AND gate that takes A and B. They're not signed; they are with 1, and creates Y, which is with 1. So we connect A and B, the inputs, to A and B on the AND cell, and connect the output Y to our wire. Then we take a second gate, which is the NOT gate, and we connect the input to this wire, and we connect the output to the output of the chip. And you're going to. That was a mistake. Okay. Okay. We can see here we synthesized the chip, and it uses one cell in the FPGA. It's got 1,000 of them, so we wasted quite a bit of the chip by just creating one of those 1960s chips. But we can, but since I forgot the programmer, and because it's really hard to show something off that's so small, we'll run a simulation instead. Okay, we're going to move it up because I'm also going to change the okay, there's nothing important happening here anyhow. But yeah, you can see here 0 and 0 and not 1, none of these. But if both of these, then the AND gate is true, and then not, so it ends up 0. So the first step to writing a language would be to just, not think so much and just write a good foundation for creating this. And I'm just going to say and cheat, and I wrote a library that allows us to generate this IL in Ruby. It looks borderline identical to the, well, I know it's identical to the IL I showed you because it's generated from this file, but you can see that it's very, very similar. It's just we wanted some point in the DSL to be able to create the DSL and know that it's syntactically correct and so on. So it's writing the foundations, extremely, extremely important. We're going to see. And then if you just program and program and program, which is something a lot of us do without thinking so much. I'm guilty, most people are guilty. We might end up with a file like this and say, like, we're actually going to show you the example first. And maybe we have something like this. Like, okay, this is how we want the language to look. It's like it has an input A and input B, an output Y, and assign Y to A and B, and then no. Right. This is what we actually care about. This is, of all that IL, this is what it actually means. We have two wires, we do some calculation on them, and we assign that to the output. And if we start, we could say, like, oh, we're just going to write a class called a module, because they're called modules for some reason. And we could just, add some things to it and just do an instance eval. Does everyone know what instance eval is? If you don't, it's probably better that way. But it evals a block inside of the context of an object. And we could just do that and have, like, make an input, and then, like, we add a port, and if it's an output, we add a port, and we just add some things, like, oh, if we add an object, we just add an object, and do some method missing. Everyone in Ruby loves method missing. There's absolutely no issues with method missing. Right, and we can just add a thing here that turns it to RTLIL. Right, how hard can it be? Pretty hard is actually the answer, because this sort of thing is extremely hard to follow because it mixes the language definition with the semantics. We kind of want to have a split where we first have something that only represents our language, and then we generate something else where we do all of the bullshit too. And this is called an abstract syntax tree. Almost all languages have an abstract syntax tree. Only very, very old implementations don't. And that's only because, like, on this C64 or something, you have 64K of memory, and every byte is really, really precious. And then you can do, like, a one-pass thing, but even if we just implemented, like, a little bit, this is, like, 130 lines, and we can, 191 lines, and we can have a small language that you can synthesize to a chip. I can show you that this actually does work. You can just see it, 0 problems, and we can simulate it again, compile it, and then, I mean, you can see it, but it's there, right? In like 200 lines, we can write a DSL that allows us to synthesize logic down into one of these. We could use this logic to make an actual chip. We could, like, Google makes something called multi-project wafers for open source project. We can send it in and get actual chips back for okay cost. We could make a completely useless chip out of this. Of course, it would be just shipping would be more than these chips, but we could literally turn this into an actual chip. But unless we're saving all of these lines. Maybe we want some extra features, and that is going to be really hard to do in this sort of thing. So we want the abstract syntax tree. So if we go back to our example, we kind of want make sure that we have this tree of objects that only represent stuff in our language. So I'm going to cheat and open. So we're going to, there's still some bullshit because I'm obviously in the wrong file. So suddenly here we have the domain specific language and the AST separated. So now the DSL itself, you can see there's only 2 methods defined on the module, and these are input, output. We use these are good, and method missing, which is if you're doing metaprogramming, method missing is actually kind of useful. And then we have a thing for the cell, and right now here I only have one method to make it more clear, but you could implement if you just replace this with another name, it's easy. And the port has and a sign. So now you can just look at this file and see what are the actual things that are valid in the language. Right now there's only input, output, and not, which is, you know, not great, but you know, for our current use it is. And then we can look at the AST, the abstract syntax tree this DSL generates. And here we still have all the other stuff that we do. And this is hidden from the language. You can't accidentally call, I don't know, add port in your DSL because it doesn't exist in the DSL. It only exists when you're manipulating this abstract syntax tree, which is not available in the example file. So the separation here between the syntax and the semantics does make the implementation a lot cleaner, and we'll see that being very important once we start adding features. And if you want like a few hundred of these methods, having the separation is very useful, and it makes documentation and so on a lot easier. So for example, this chip was kind of boring, but most importantly because this doesn't depend on a clock. Clocks are the most important thing in digital logic. You kind of care about clocks, like your processor has clock cycles, right? And right now we can't have clocks, but we kind of would want some clocks. So I'm going to show you. Oh shit, because I selected the wrong one. Okay, give me a moment. That's what I get for, so, maybe we want this chip. This is a 7469 timer. Not a timer, counter. What it does is, on the clock cycle, it counts up. 0, 1, 2, 3, 4, 5, 6, all the way up to 15. And there's a reset. It's got an asynchronous reset, which means it can reset outside of the clock cycle. And for some reason, because this was in the 60s, they decided that they have negative clocks, which means that when the clock cycle goes down, that's when it's important. Usually the default would be to have a positive clock edge. We care of it when the clock goes from 0 to 1. But in this chip, we only have one output. Let's say we want to add width, and we wanted to reset to 0, because, yeah, that's what counters do. And then Q should become Q plus 1 continuously. But this only makes sense because the logic is not combinatorial. It is. We need some sort of magic device here. And the magic device is the second thing that's important in these chips. All of these 1,000 lookup tables that we have contains a D flip-flop, a data flip-flop, which is like a very small register. It contains 1 bit and, or in this case 4 bits, but yeah. So in the DSL, we kinda only, okay, this is because I'm in the wrong file. It's very important to be in the right file, otherwise we need to add the clock thingy so we can set how the clock works. We need to add here how the reset works. And we didn't have add before. And we also had another secret new feature, which is we can add constants. We need to support constants. That's suddenly very important. But you know, the file looks very, very similar, and that is the goal of separating out the abstract syntax tree from the actual language. So we want to make sure that Q has the old value all the time until the clock goes negative. Then we go into our AST, which contains an AST walker in itself. You probably would have a walker that is outside of the abstract syntax tree if you were doing it more seriously than me. But except for adding like a little bit parts here, but setting the clock and setting the reset value, we're going to see that because of the separation we have, there's very little new. We add some new wires for the clock and the reset input. And we create a new cell for each output that is a D flip-flop. In this case, an asynchronous D flip-flop because the reset is asynchronous. Not important. And we create a new cell for each of these. And we add a new thing. You can have constants and with widths. And then the only small change here is handling constants. And that I can't see because I'm not looking at my own screen because I'm a complete idiot. Oh, okay, and here. When we're writing to a thing, we should be always writing to the next value of the flip-flop and reading from the old value. But, you know, small changes. I can show you that. We're probably not going to want to use the Y argument because it's not going to work out very well. Diff-y creates a 2-line thing. But yeah, there's like a small, we added some very major new features. It's like 50 lines of changes or so. And that is the, and by separating these two, we I'm talking a lot about the abstract syntax tree, so you remember that word because that is the word you should Google for. And so, and yeah, that is pretty much everything you need to make a like a full chip. This is like the sort of cells that the Intel CPU in this thing is designed from. They have more of them, of course. They didn't just use NAND, NOT, and adders. They used hundreds of these cells. But it's pretty much the same. They probably have 200 cells. We used 4 different kinds. And see, this time we used a few more cells in this. It used 11 cells. Two carry cells that carry data from one bit to the next. D flip-flop, and 5 lookup tables. But yeah, it's still a tiny chip. It only uses 11 cells because it does so little with each of them. We could jam in a lot more logic if we really wanted. We have a test bench here that's a little bit more used to. I can show you the test bench I wrote. This is probably the test bench. It first resets the chip, and then if the cycle is evenly divided by 100, it resets the chip. Otherwise, it toggles the clock and prints out what the value of the counter is. Yeah, that worked. Presumably, it should start on 1 because I run the clock before printing out. So 1, 2, 3, 4. Okay, that was a bit much. So 15. Then it turns to 0. Turns to 15. 0, 15. And then at 100 it should reset. Yeah, it goes from 4 to 1 again. 200. 4 to 1. So we're going to go from 4 to 1 every time, I guess. No. Yeah. That is, of course, because 16 and 100. Okay. But anyhow, so now you know that you can also make your own chips, and that is fun, exciting, and it gives you Fox errors. And you can also write your own language. It's useful for anything, like from search in your app to your own database to ETL, a lot of businessy things. It's probably super useful. I use them a lot because it allows you to separate the logic from all the bullshit in the middle, and I really enjoy that pattern. So yeah, any questions? You weren't as violent as I thought you were.
So how many of those little FPGAs and how much code would it take to make something recognizable like an 80s microcomputer?
Like a 6502 or something is probably like 100 lines, maybe.
Okay, that's just the processor. That's just the CPU, right?
Yeah. But like for example, an Apple II, it's probably like the support chips is probably another 100 lines, but it's like eminently doable in an evening. The hard part is of course like an 80s microcomputer contains a lot of analog logic, which an FPGA cannot do, or at least these FPGAs cannot do. There are special ones that contain analog cells. But these ones only contain digital logic and memory. So like generating a TV signal and so on has to be done externally. But yeah, it's like 100 lines to make like making an Amiga each chip is probably just a few hundred lines of code. They are very simple. Like 80s computers are very simple. And you can make like a RISC-V CPU in an evening. It is not as hard as people want it to be. Of course, most FPGAs aren't used for prototyping actual chips. They're used for the fact that they have ridiculous amounts of I/O. So even though, like, I have the more intensely I/O intensive version of this board, it's just bigger, and it's got hundreds of GPIO ports that you can toggle at hundreds of megahertz, which is faster than any microcontroller that you can ever find. Like, it's faster at toggling pins on a €30 board than, yeah, like this Intel CPU is. So they can toggle pins really quick, and that can be useful for some things, like sensor fusion and so on. But what I use them for mostly is replicating chips that I could never get actually made. Like, we talked about the Mister, for example, which is a project that writes these little snippets for arcade consoles, arcade machines, retro computers, and turns one of these into an actual computer. Any computer, and you can swap on a moon nowadays. That is my fault. But yeah, that is the point. And these are super fun. They're like €30 for a good dev kit. They're very nice. FPGAs are fun. You should do more hardware stuff. Soldering is good for you. There's a big asterisk on that one. Yes.
If I want to learn a bunch more, where do I go?
But what specifically? Domain-specific languages or hardware?
DSL to start with, I think.
No idea.
Okay.
Google. There's a book actually.
Tools that you were using here today, for example.
I have not used any tools, except Josys. Josys, if you're doing FPGA stuff, Josys, excellent stuff. I'll show you how it's spelled. Josys. Okay. But otherwise I just use Ruby because I'm lazy. But yeah, there's a book actually that I've read recently that's known as Crafting Interpreters. It's not on exactly the same topic, but it's very much overlapping, and it seemed pretty good.
Okay. Could you share some links, resources afterwards?
Yes, I'll make up a thing.
That would be awesome.
Yes. I'll also make up a GitHub repo. I didn't have the clarity of mind to do that beforehand. For some reason. Yeah.
So you showed and not, the logic for these.
Yeah.
How the actual electronics works in the middle. Didn't seem to cover it. What other methods do you have on your chip?
Okay, so
how complicated does it get?
it doesn't get very complicated. This is the internal cell library of Josys. So we have the NOT gate, the POS gate, NET gate. These are just take and of all the bits. It's not so complicated. Here we have the binary cells, which are AND OR, shift left, shift right, logical AND, logical OR, equals, not equals, and so on. This is the cheaty ones, division, which is actually hard to implement yourself, multiplication, modulus. There's also an exponent one. You probably should never use that one, but in theory they exist. And then there's multiplexers, which is, it's this cell. It does, if S is true, it takes B, otherwise it takes A. And then there's the registers that we used. There's 2 of them. There's SR and DFF. Set reset is one, and the other one is a data flip-flop. And that's actually it. Like, that's the cells. There's some cheaty cells as well. There's memories. These aren't in, they are in the FPGA, but they don't exist in, like, they are synthesized to a larger degree.
So when you want to write more complicated programs and have functions and
you can,
do you have to write
but they have to
DSLs
combine down into these, because you can't have, like, hardware doesn't do function calls, right? What is a function called in hardware? Doesn't matter. So now you have these. So you have the memories, and this is everything you have in an FPGA. And some of these are extremely limited, like, for example, multiplication. In this, I think there's 1 multiplier, and you have to use it well. And division, just, if I try to synthesize division in this, it's just going to say, haha, fuck you. But the fancier hardware you have, they might have more advanced black boxes. We call them black boxes because they can be literally anything. And they are special cells that exist, like a floating point unit or an ARM processor and so on. They can exist within the FPGA fabric. And you can link those up to your stuff. But generally, you only have access to these, and that's as much. And if you want to make like an if statement, you have to, that's actually a mux and possibly a flip-flop. If it's just an if and there's nothing else. And so it's very little. You have to figure out yourself how to turn iterative things into combinatorial things.
Yeah, I think that's it. I think we're done.
Yeah.
Thank you so much.
You're welcome.
So thank you all for coming, obviously, and thank you to our host, Karnov Group, who is looking for Ruby engineers. If there are any here who might be interested, that would be cool. Talk to Chris about that, and great to see you all.